Welcome back to Calculus 2, Section 3.4, Partial Fractions. We have a number of topics to go over. We're going to begin with looking at integrals of rational functions. We'll start with a little algebra review. Suppose that we have two rational functions, 1 over x plus 3 and 1 over x plus 4. We take the difference. We can do algebra. We can combine these two rational functions into a single rational function by multiplying each rational function by 1. The first rational function multiplied by x plus 4 over x plus 4. The second multiplied by 1 in the form of x plus 3 over x plus 3. That will give a common denominator. And combining in the top, we can simplify and produce a single rational expression. These two then are equivalent. Let's do a little vocab review. In the bottom, we have a product of two binomials. Each binomial is a linear polynomial. Since they are being product, we can refer to each as a factor. As each is degree 1 as a polynomial, these are linear factors. Their product is quadratic. The trinomial x squared plus 7x plus 12. That's the product of the binomial x plus 3, the binomial x plus 4. Good. Now, on the right-hand side, we have this rational expression. It's a rational function. And on the left-hand side, we have a difference of two rational expressions where the denominators are the linear factors of the quadratic denominator on the right-hand side. Good. So the left-hand side, therefore, we're going to phrase that as a partial fraction decomposition of the right-hand side, this rational function. What we have done is we've gone from, by algebra, this left-hand side produced the right-hand side. In this section, we're interested. This notion of partial fractions is going from a rational function and producing a sum or difference of elementary rational functions. That's called partial fractions, the method of partial fractions. We want to start with a rational function and produce simplified versions which are equivalent to it. Good. So let's take this partial fraction decomposition. We have the rational function as integrand, which we can break up in its partial fraction decomposition. And then we have integrands, which are elementary integrals after a u substitution. So, integral of dx over x plus 3, we can use u equaling x plus 3, come up with the natural log of the absolute value of x plus 3. Likewise, for dx over x plus 4, it will turn into ln of absolute of x plus 4. That will evaluate the integral. And so, don't forget the constant of integration, c. Good. This is thanks to partial fraction decomposition that we're able to take what would otherwise be a head scratcher and simply evaluate integrals. Excellent. Let's do some more examples. Looking at this rational function, in the numerator, we have the variable plus a constant 4. We have the variable plus 3. We know that 4 is 1 bigger than 3. We can take 3 from 4. We're left over with 1. Then if we look at x plus 3 over x plus 3, that turns into 1, and we know that 3 plus 1 will give us 4, so that the numerators equate. And then we are in the situation where if we put an integral on all of this, we have two integrands which we can easily evaluate. 1 as an integrand will go to x. 1 over x plus 3 will go to ln of absolute of x plus 3. Beautiful. Let's try another. All right. Take a look at this denominator and numerator. Note that in the denominator, we have a linear polynomial. In the numerator, we have a quadratic polynomial. The example that we just did was this notion of dividing the bottom into the top. And since the top has at least a degree as high as the bottom, there's some division to be accomplished. And if we do that, dividing x plus 3 into the top, we'll come up with x plus 1 as the quotient and negative 2 as the remainder. You can verify that. If you multiply x by x plus 3, you'll get x squared. That cancels away. And 3x and 4x have a difference of 1. Thus, you'll need another 1x to form up the 4x. And one copy of 3, taking the difference of 1 minus 3, gives you negative 2. In other words, I just performed long division. With that integrand, we can evaluate. The x goes to x squared over 2. 1 goes to x, and negative 2 over x plus 3 goes to negative 2 times ln of x plus 3 in absolutes. And as this is an indefinite integral, we always pick up a constant c. Very good. Another example. Now, looking at the degree of the top, it's degree 2. The degree of the bottom, it's degree 2. We again want to think about dividing the bottom into the top. And if we do that, we'll come up with, and this is similar to the example previous, that there's x squared. You can combine that with 3x. And then if you subtract away 5, you'll be left with negative 4 to match up to produce this 1. But subtracting 5, you should also add 5 back in. And since we only used 3 of the 4 x's, we also have an x remaining. Nice. So the 1 is going to give us an elementary integral. The x plus 5 quotient, x squared plus 3x minus 4, is going to require some work. And that's where partial fractions comes in. But note that we have taken a degree 2 over degree 2, and by simple algebra, reduced it down to a nice quotient, which we can integrate, and then a piece that we have to apply the method of partial fractions to. So you know that you want to begin partial fractions when the rational expression has a degree of the top strictly smaller than the degree of the bottom. Degree 1 versus degree 2. Good. In other words, we can use the vocab. On the left, we have an improper rational expression. And then on the right, we have a nice quotient plus a proper rational function. And by that, we are considering the degrees of the top versus the degree of the bottom. Good. So before jumping into the method of partial fractions, go back and review that you can evaluate these integrals using simple algebra techniques. Good. We're going to begin the method of partial fractions with the assumption that the denominator will factor into distinct linear factors. For example, rational function x plus 5 over quadratic x squared plus 3x minus 4 is proper. The top is degree 1, the bottom is degree 2. And the denominator factors as binomial x plus 4, product binomial x minus 1. The linear factors are distinct. We can then set up partial fractions by taking the rational expression and decomposing it into a sum of proper rational functions. If the bottom is degree 1, to be proper, we want the top to be degree 0, i.e. a constant. Since the factors are distinct, these will be distinct rational functions. And our job is to determine the coefficients a and b. Well, let's go ahead and get rid of the denominators. So x plus 5 will equal a product x minus 1 plus b product x plus 4. And then to determine the coefficients a and b, we'll have two methods. Let's go over the first method, called the method of strategic substitution, which is you look on the right-hand side and you think, how can I eliminate one of the unknowns, a or b? I can eliminate the a if I let x equal 1. So if I let x equal 1, then the left-hand side is going to become 6, and the right-hand side will be b times 5. You can easily solve for b. Do that once more, but this time eliminate the b term by allowing x to be negative 4. Come up with the left-hand side as positive 1 and the right-hand side as negative 5 times a. Very good. We've thus solved for the unknown coefficients a and b. And we can take our proper rational function integrand and express it out as a sum of rational functions which, as integrands, have simple evaluations. You can do a u sub of u equal x plus 4 and a u sub of u equal x minus 1. And then we come up with our evaluation. And we're done. Looking good. So this example that we just did generalizes anytime that you have an integrand which is proper, the degree of the top is strictly less than the degree of the bottom. And when you look at the bottom and you factor it, the example that we did, we had two distinct linear factors. But more generally, it applies anytime that Q has n distinct linear factors. Then the partial fraction decomposition will be a sum of n proper rational functions. Let's take a look at that. If P over Q is proper, and that if q has n distinct linear factors, then we use each of those linear factors as a denominator to come up with a sum of proper rational functions, meaning that the numerator for each of these rational functions is degree 0, where the denominator is degree 1. And then once this is set up, your job is to then determine these unknown coefficients to come up with the partial fraction decomposition. Beautiful. Let's do another example. Let's look on the left-hand side. Look at the numerator. The numerator is quadratic, that's degree 2. The denominator is cubic, it's degree 3. The denominator has already been factored into linear factors. Each of the 3 linear factors is distinct from the other 2 linear factors. Thus, the left-hand side can be expressed out as a sum of 3 proper rational functions, each of which has a denominator given by one of the 3 distinct linear factors of q. Fantastic. And then whenever you have distinct linear factors, you can use the first of our 2 methods, the method of strategic substitution, in order to determine coefficients, a, b, and c. So here's an example for you to work. Very good. Now, we've looked at distinct linear factors. Let's consider the case where q has repeated linear factors. Let's take a look. All right, so we're again going to assume that we have a proper rational function as integrand. Degree of the top is strictly less than the degree of the bottom. But now let's assume that q has some linear factor, but that linear factor appears more than once. Let it appear n times for n greater than or equal to 2. And then what you want to do is you want to add in a proper rational function where the denominator is that linear factor raised to integer powers running from 1 to 2, out to n. Okay, let's do an example. All right, so here we have an integrand. The degree of the top is 1, and 1 is smaller than the degree 3 of the bottom. Therefore, this is a proper rational function. The denominator q has 3 linear factors, but 2 of the 3 linear factors are the same. Let's see how that affects the setup of partial fraction decomposition. When we go to each linear factor, if it is distinct, then it appears once in the bottom and is the denominator of a proper rational function. We go to the next linear factor. It's distinct from any previous. We set up a proper rational function. But when we go to the next linear factor, it happens to repeat. So what we do is we use 2 copies of that repeating linear factor. And note carefully that the numerator remains degree 0. So for example, if our q was actually degree 4, x minus 2 quantity cubed, for example, we would need to add in a fourth term in our partial fraction decomposition, which would be d over x minus 2 raised to the third. Okay, good. So this is the form of the partial fraction decomposition, and we now want to find a, b, and c. So we multiply both sides by q to clear the denominator. We come up with x plus 1 equals a product x minus 2 quantity square, b times x plus 3 times x minus 2, and then c times x plus 3. Good. Unfortunately, we are not able to use the method of strategic substitution. We need to now go over our second method for determining coefficients. And that is the method of equating coefficients. Okay, so let's take a look. So here's where we were. We've cleared the denominators. Now what we want to do is multiply out, do algebra, x minus 2 quantity squared, multiply that out, binomial x minus 2 times binomial x plus 3, product that, and we have x plus 1 equaling this sum of 3 terms. What we're going to do is we're going to now distribute the coefficients a, b, and c, and then we're going to record terms in descending powers. Let's start with quadratic terms. So if we first begin collecting only the quadratic terms, distribute the a, distribute the b, these are the only 2 quadratic terms that we'll produce. That's power 2. Next, let's look for all linear terms, distributing a, b, and c. Linear terms would be these 3. One from distributing a, one from distributing b, and one from distributing c. And then finally, collect all constant terms. Okay. Now that we've done that, let's look at this right-hand side and go power by power, equating the expressions on the right with the expressions on the left. Let's start with quadratic x squared. On the right, we have a quadratic term with coefficients a and b. And we can set that equal to the coefficient to x squared on the left. Well, there is none, so let's introduce it as 0 times x squared. Then the coefficient on the left is 0, and the coefficient to the quadratic term x squared on the right is a plus b. That gives us one equation, and these are the coefficients to the x squared terms on the left and right. We can then come up with a second equation by equating coefficients to linear terms. So on the left-hand side, the linear term has coefficient 1, and on the right-hand side, the linear terms are with coefficient negative 4a, positive b, and c. Good. So we have coefficients for the quadratic term, coefficients for the linear term, and then we equate the constants on the left and on the right. We're looking to solve for 3 unknowns, a, b, and c. And we now have a system of 3 equations. So we proceed and we solve. The very first equation is going to allow us to express out all a's in terms of b's. And then by doing that, we have a system of two unknowns and two equations for those two unknowns, allowing us to then solve for the b and the c. And then knowing what the b is, we can use our first equation to write down the a. Okay, so this is the second method. We're equating coefficients, whereas the first method was strategic substitution. You need to use this second method of equating coefficients whenever you have repeated factors. Nice. Now, with a, b, and c identified, we can take our integrand and write down its partial fraction decomposition and have nice elementary integrals to evaluate. So the constant over x plus 3 will integrate to ln of the absolute of x plus 3. Same thing for the x minus 2. And then using a u substitution for the x minus 2 quantity squared, letting u equal x minus 2. That'll be u to the negative 2, which will integrate up to negative 1 over u. Beautiful. That finishes that integral. And we've gone over our second method for determining coefficients by equating like coefficients. Here's an example. The integrand is a proper rational function. The denominator q will factor with repeated linear factors. You'll then want to use the method of equating coefficients to determine the partial fraction decomposition. Very nice. So when you have distinct linear factors, you can use strategic substitution. If you have repeated linear factors, you need to use the method of equating coefficients. Let's make the statement for the general method. To the examples we've done, we'll have to address the case of quadratic factors. Here is the full statement of the general method. It looks like a lot. Let's go through it one by one. The very first thing that you want to do is you want to make sure that the integrand is a proper rational function. If it's not, you use algebra, long division, to produce a quotient. And then a remainder will give you a proper rational function. You'll look at the denominator, q, and you'll factor it into linear factors and irreducible quadratic factors, possibly. The factors of q are going to determine the decomposition of the quotient. For the simple case, where all of the factors are linear and distinct, you'll use each distinct linear factor to form a rational function, which is proper, and then use the strategic substitution method to determine the coefficient numerators. If q happens to have repeated linear factors, then the decomposition will contain a proper rational function where the denominator is the linear factor raised to integer powers ranging from 1 to n. To determine these numerators, you'll want to use the method of equating coefficients. Good. We have not yet addressed, and we will address next, what to do in the case of quadratic factors. Well, you want to know that this applies to irreducible quadratic factors, an example of which would be x squared plus 1. X squared plus 1 does factor, but you must resort to complex numbers. So I squared is negative 1 plus 1 makes 0, so I is a root. But as this is introductory calculus, we limit ourselves to real numbers. Hence, this is irreducible over the real numbers. In such a case, let's back up. In such a case, the term in the partial fraction decomposition will take that irreducible quadratic factor and to form a rational function with that denominator, we can allow for as much as a linear numerator. Thus, the numerator will be an unknown coefficient a on x, and then any constant b. All right, good. The last part is that if we have an irreducible quadratic factor and it repeats, then like we had in the repeating linear factor, we form up rational functions where the repeating irreducible quadratic factor appears to a power ranging from 1 to n. Very good. Let's do an example. Let's do an example for the quadratic factor. Here, our integrand is proper. Degree of the top is 1, degree of the bottom is 3. When we factor the bottom will factor as x product x squared plus 1. X squared plus 1 is irreducible. So to form up the partial fraction decomposition, linear factor x will have numerator unknown a. Irreducible quadratic x squared plus 1 will have numerator unknown b multiplying x plus an unknown c. We now want to find the coefficients a, b, and c. Just as before, we begin by clearing the denominators. Multiply by q, produce x plus 1 equals a product x squared plus 1, and bx plus c binomial times x. Distribute out the x, get bx squared plus cx. Very nice. If we equate corresponding coefficients, on the right-hand side, we have quadratic terms with coefficients a and b. And on the left, the coefficient to x squared is 0. Linear terms on the right, we have a c, and on the left, we have a 1. And then constants from the left, we have 1, and on the right, we have a. Very nice. This has produced the value for a, the value for c, and with a equaling 1, b will equal negative 1. Very good. So we can plug this back in and find that our integrand has partial fraction decomposition 1 over x plus negative x plus 1 over x squared plus 2. Use that to express out the given integral as the sum of integrals dx over x, that'll evaluate to ln of absolute x, and then rational function negative x plus 1 over x squared plus 2. And then this will break up into two separate integrals. if we look at negative x over x squared plus 1, we can substitute with u equaling the denominator. U equaling the denominator, we'll find that du is 2x dx to match up with the x in the numerator. And then placing 1 over the denominator is an elementary integral, arctan of x. Very good. Here's an example for you. And next we'll look at setting up the partial fraction decomposition. So here we are going to have x squared plus 1, which is an irreducible quadratic factor, in a repeated form. Let's begin with the integrand and look at the repeated linear factor. This is x minus 0 quantity to the third. So we'll pick up in the partial fraction decomposition the terms a over x, b over x squared, and c over x cubed. That's the repeated linear factor. Let's look at the repeated quadratic factor. We'll have that quadratic factor as a denominator. In the numerator, some unknown dx plus e. And then because it's repeated, we get one more term, the irreducible quadratic raised to the next integer power with a similar numerator, unknown f on x plus g. Only repeats twice, so we've picked up those two terms. And then finally, the last, x minus 3, is a non-repeated linear factor, so we just pick up an h over x minus 3. Excellent. So that is the setup of the partial fraction decomposition. To do the algebra and find these unknown coefficients a through h is quite a bit of work. And we don't benefit all that much by employing all of that algebra. It's the setup which is important. So you give it a try. The denominator q has already been factored. And there are linear factors which repeat and quadratic factors which repeat. Come up with the partial fraction decomposition, the setup for it. Do not solve for the coefficients. That brings us to the end of this section on partial fractions. Thank you so much for watching. Please like if this is useful to you, and I will see you on the next one.